Thanks, Mr. Bones. I needed that inflated. We'll be using this later. Hi, everybody. Welcome back to science. This is week 5, and this week we're going to be talking about the 4 fundamental forces. Now, a few weeks ago, we were discussing the states of matter and what matter is, and we're going to start this lesson by talking about one of the core pieces of matter, which is the atom. Now, the atom is made up of 3 components. It's a neutron, a proton, and an electron. The neutron and protons, they hang out in the center in the nucleus, and the electrons float in a cloud of energy outside of that. But what happens in between those elements, as well as what happens when you get a whole bunch of them together, how does it affect our world and our universe? So, in the beginning, there was the Big Bang. And from the Big Bang came basically 4 judges with giant gavels, because all of those subatomic particles were out there floating around everywhere, and someone had to give it order and had to figure out a way of bringing them all together so our universe could exist. And those 4 judges were the fundamental forces. There's 4 of them. There's the strong, there's electromagnetism, there's weak, and there's gravitational. And those forces rule and make the laws that all matter and all energy in the universe obey, and they follow, and they keep to it. And as far as we know so far, none have broken it, although science is still looking out there and saying, but right now, this is it. These are the laws. This is what their gavels came down and put in the books, and what every particle follows. So the first one we're going to talk about is the strongest force, which is called the strong force. Science is great. Sometimes it tells you exactly what it's dealing with. The strong force uses force carriers called gluons, which are those subatomic particles that we think about when we're talking about the functional building blocks of everything. And gluons hold protons and neutrons inside the nucleus of the atom. They only cover short atomic distances, and short atomic distances are tiny, 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 tiny little specks of space. So tiny, it's not a foot, it's not an inch, it's not a nanometer or millimeter. It's so tiny, it's between 2 particles that make up the atom, the proton and the neutron, and it holds them together and keeps them bound, much like Velcro. So if you have Velcro on your shoes or on a jacket, you can use this, and this is a really good representation of that force. So you would take the 2 sides of it, and when they're out here, hi, I'm just 2 protons hanging out. I don't want to be next to that proton. I'm just out here fluttering around. But when they make contact, you can hear it's really hard to pull them apart. And when they do, it makes that huge sound, and that big release of energy happens. Because Velcro, nothing, and then, boom. That is a great representation of the strong force. All right, the next force we're going to talk about, electromagnetism. So electromagnetism uses a force carrier called a photon, which we see in light all over the place. But we don't realize this when we're heating up our food in the microwave. That's using electromagnetism as well. It also is what helps protect the Earth. So it's not only small, but it's also huge. And the Earth is a giant solid with a molten core of heavy metals that are churning around and creating this big electromagnetic field, which protects us from all sorts of things coming in from the universe, including from our own sun. When there's like solar flares, it helps to deflect it so that life can exist on our planet. So along with the photon has a very simple principle. Alike things don't attract, dissimilar things attract. So if you have 2 things that are positively charged, they don't want to hang out. You have 2 things that are negatively charged, they don't want to hang out. But you have 2 things of opposite charge, like if you look on a battery, one side says plus, the other side says minus. Plus, minus, positive, negative, they attract, and they will always attract. Which leads you to go, wait, protons are both positive, and they're hanging out together, right? They're trying to push themselves apart from each other. They're trying to separate, but that strong force is stronger than the electromagnetic force trying to pry them apart. So that's what helps to hold them together. That's why this is the strongest of forces, and this is the next strongest. It's also what's used when the electrons are on the outside, and that electron cloud, that energy, they want to come to the center too, because you have positive, negative. Electromagnetism is what holds it out there. The cool part is, what's keeping it from coming to the center? This is one of the neatest pieces of energy out there. The weak force. Now the weak force has two subatomic particles that it uses as force characters, the W and Z boson. It's so important it takes 2 to do this job. So this is the one that pushes back and keeps the electron from coming to the center. It's also the one which provides a very important role of allowing those subatomic particles to move between atomic particles. So they can move between protons, they can move from neutrons to protons, they can move outside of the atoms and create new elements. They can be shared between two different atomic structures to create a third. Very similar to, I have here a little atom, my atom of yellow, and I have here my atom of blue. So I have my yellow and blue atom. So what happens if I mix my two yellow and blue atoms together? They turn into a giant green atom. So these two atoms, there's nothing left in them. They've shared, and now they've turned into one giant green atom. So that is it's a representation of the weak nuclear force, right? So now we move on to gravitational. Now, gravitational force, we experience it all the time. It's what keeps us from flying off the planet. It's one of the forces that keep us from flying off the planet. But it's got an interesting thing that it's based on. Right now, we think there's something called a graviton out there, and only in, I believe, 2016 was the first time we ever measured a gravitational wave. So by measuring the wave, it tells us that there's probably a particle or a piece of energy out there that we've only theorized, that we've called the graviton, that's creating that energy wave moving through the universe. Now, gravity goes out infinite distances. So if you're at the edges of our universe and you can detect gravity waves, you can detect our planet. It just goes on and on forever. It's also interesting because it always attracts. It doesn't repel. Atoms always want to come at each other. They always want to group together. Mass wants to group on mass. Matter wants to group with matter and create these huge solids, just like our planet. And this is another cool thing. It's not based on size. It's actually based on how much matter is contained in one area. So the Earth, decent sized planet. I kind of dig it. I'm having a good time here. But there's also Saturn, just up the way. Now Saturn's huge. Saturn is massive. It takes 764 of our planets to fit inside that planet. So Saturn's like a giant gas giant balloon, and if you took a whole bunch of marbles the size of Earth and put them in there, it would be 764. Cool thing is, we have almost the same gravity. So the size of the object doesn't matter, it's the amount of matter that's inside of it that matters. So it's the amount of matter that matters. Cool. Just like, this big heavy brick. It's about 15 pounds on Earth. Now, if I walk onto the moon right now, it becomes about 2.5 pounds. Because does this change? No, it stays the same. It's the same big hunk of concrete that it is right here on Earth, but because the planet I'm near is so much smaller, the surface is smaller, everything about it is so much smaller, and it's compacted the same way, it just has less gravity. Less mass, less matter, less gravity. So, here's one of the experiments I'd like you to do at home. So this is for the photon. This is for electromagnetism. Take a dark piece of construction paper. I happen to use black. If you have any other color, just a dark color, and take a light piece of paper, and I cut this one out to be like our friend, the photon. Hey, it's a little force carrier, the photon. And I'm just gonna put it on top. I might even put a little piece of tape under it to keep it there, and then put it in the sun. Leave it in the sun for about a week and see what happens underneath the light piece of paper versus the dark. Look at the difference in what happens as the sun is affecting it, and the electromagnetism, those photons are going to hit the surface and they're going to start breaking down the atoms in the dye. They're going to start breaking apart the weak force and allow those subatomic particles to break off and change the color of it. I'd like to see what colors you come out with, and hopefully we'll get more sun than we have today because it's kind of raining today. Another experiment you can do is, if you have a balloon, this is a cool one, and I like doing this one a lot. You get a piece of wool or even your hair, and you kind of rough it in your hair. And what you're doing is you're transferring the electrons in your hair onto the surface of the balloon. And then hopefully it will stick to a surface. And it'll hover there for as long as it can, as long as there's electrons that can bind it and hold it there. The wall and this are sharing those electrons, and it will stay put. And those are just some cool experiments that you can do at home and we'll be doing in class, and have fun with it. And let's see what happens over a week, because we can all set those pictures up, put them in a window, and then next week when science happens, we can check them out again. Bye.